I call it electron correlation. But not only electron correlation, but sort of electron correlation the wave function way. Because after the 2 weeks with me, I think Gemma comes and is going to talk with you about DFT, density functional theory. So I sort of add a subtitle to that, typically getting it right for the right reasons. Gemma might want to comment on that. You had Hartree Fock theory last week or the week before. So in Hartree Fock, we have, of course, a Hamiltonian, or we have this Fock operator. And there's, I guess also in this book, there's a little small f and a large f. And the small f is a one electron operator. Typically, one electron operators, one electron functions are written with small letters. And the capital ones are many electrons. So this capital F is the sum of all Fock operators. One could also call it Hartree Fock Hamiltonian. And that's the H, that is sort of the Hamiltonian which we get from quantum mechanics. And then we have a one determinant wave function. It's a single determinant, meaning an antisymmetrized product of spin orbitals. We also call often SCF, I mean Hartree Fock is often called SCF theory, self-consistent field theory, as you hopefully learned. And it is sort of self-consistent field, but much more important in a way, it's a mean field theory. Because the electron moves in the average or mean field of all the other electrons. So you have electron-electron correlation. I mean, they are repelling each other, but it's an averaged of the what is called the instantaneous correlation. So you only have the average electron-electron interaction described by this Fock operator or by the part of the Fock operator, which is the potential, the Hartree Fock potential. And as I said, there is a once later determined wave function, and that one determinant wave function corresponds to an electron configuration. Let's take, for example, the beryllium atom with 4 electrons, and if you look at the periodic table, you can see that the better ones, they write something like this as the electron configuration. And that really corresponds to the Hartree Fock wave function for that. Single determinant Hartree Fock wave function. But that also the other way around means all those electron configurations which you can see in the periodic table, these are just sort of one determinate wave function. That's the very lowest approximation to the wave function of those atoms. If you want to get really high quality results, you can't just approximate it with a single determinant. So that's one configuration. Surprisingly, that this is only one determinant or configuration, and if you really want a good result, you have millions of them. You still get a very good result. You get with Hartree Fock maybe about 99% of the total energy. Recovered by Hartree Fock. The problem only is that, so you miss something, you miss the 1%, and that 1% we call an electron correlation, or if you say with the total energy, if we would solve the Schrödinger equation exactly, if we could do that, that's then sort of the Hartree Fock energy plus what is missing, which we call the correlation energy. And that's about 1% which is missing. Unfortunately, that 1% is sort of in the interesting range for chemistry. So the motion of the electrons is not independent of each other. And on average, sort of, if you really look at it, the electrons are on average farther apart than you have in Hartree Fock. And that's what we call electron correlations. And now there are several ways we can improve on Hartree Fock. And one way is the one we're going to do in these 2 weeks, and the other one is going to be density functional theory. We're going 2 ways. So we have 2 ways. Improve on Hartree Fock. We could go the way to what is called CompChem DFT, where we have that the energy is a function of the electron density. That's sort of the essence of density function theory, that you can express the energy as a function of the density. But CompChem density functional theory, you still have a Fock operator like you have in Hartree Fock, and you still have a one determinant wave function, many electron wave function. That's still there in CompChem DFT. I mean, there's also real DFT, orbital free DFT, but that's not the one you're going to use. The one we all use, most of chemists use, is actually density function theory with orbitals, with the Slater determinant, and with a Fock operator, which is very much like this Fock operator, but slightly different. So what you basically do in DFT is you keep the one determinant wave function like you have in Hartree Fock, so you don't improve on this issue, but you fiddle around with the Fock operator. You make that different, which means that's not like in the full Hamiltonian. So there are extra terms in here which Gemma is certainly going to talk with you about, which then bring correlation in this way. So here you play here, but you keep this one. The problem is that here there is no hierarchy of methods. There are plenty of functionals. The exact functional, the exact relation is unknown. That's okay, but there's no way to get there. I mean, there's no hierarchy. If you have one functional, then you know this one is a higher level functional. In a way, they are sort of all equal. And that means if you don't like the result you get with one functional, you don't know how to improve on it, except trying a lot of other ones. So there's no hierarchy of methods. Quite contrary to what we are going to look at now, and that is wave function theory. In wave function theory, we have the original full Hamiltonian, as you know it. But what we change, so we don't play around with the Hamiltonian. What we change is we replace, having instead of one determinant, we have now a lot of determinants. A lot of Slater determinants. And therefore it's called wave function theory, because we do something with the wave function. And here we have a clear hierarchy of methods. Actually hierarchies, because there are sort of, in a way, 4 types of methods, 4 types of hierarchies, in which way we can get to a more and more accurate wave function, which unfortunately always means a more and more expensive wave function. But I mean, that's the way it is. So in principle, you always know, if your result is not good enough, you know how to improve the accuracy, which does not always really help you, because you might not be able to do the calculation then. at the next level of theory. But in principle, you know, okay, if that method doesn't work, then I should go this method. Right. In most cases, if you have larger systems to treat, nowadays this might change eventually because people are working on making those methods more efficient. But in most cases nowadays you're going to use DFT for calculation on large systems. That's sort of okay. There are also nice aspects. You have orbitals, so you still can make orbital pictures if you like that. Inorganic and organic chemists typically like that. But you should sort of be aware of that. You don't really know where you are. And from time to time you should check whether the quality you get here is good enough, and there where wave function methods can come in again. On test systems you can check the accuracy of doing those calculations by doing a more expensive wave function calculation. Another way, for example, you all had already sort of something about geometry optimizations. What is done a lot nowadays is you do geometry optimizations at the DFT level for your reactants, products, transition states, but then you improve the energies at those geometries by doing a wave function calculation. So you save money and time by doing the cheaper DFT geometry optimization, but when you want to get the energies in order to calculate reaction energies or energy of transition states, you do a single point wave function calculation at that geometry. And one important point, you had maybe basis sets last week, didn't you? There's a clear difference in the dependence on basis sets. DFT has a slightly different dependence, and the dependence is much less than here. Meaning, unfortunately, not only are those methods more expensive, but they also depend more on the basis sets. So you have typically to use larger basis sets. Of course, I would assume the author of your textbook is making the point in that chapter that for DFT you should of course use his basis sets, which are made for DFT, and not those correlation consistent Dunning basis sets which are actually made for this kind of calculations.